Hey everybody, the purpose of this video is to get you some solutions very quickly, actually, it won't take very long, about the variation quiz about Chebyshev's theorem. It's one of those ideas, sometimes I do it in class, sometimes I don't. In most recent years I've decided not to because, honestly, although it's fine and dandy, and it's a wonderful result, I'm not trying to discount what Chebyshev was able to come up with. Since so much of what you guys are going to study in your lives generates from normally shaped or roughly bell-shaped data, there's really no need for something as general as Chebyshev when you can use the empirical rule, the 2/3, 95, 100 rule. So there's really not a whole lot of a point of worrying about it. But those of you, some of you have been asking, and I've been telling you there's a quiz for it, but you've been asking, what if the data is not bell-shaped? That's a great question because there's a big if. If your data is bell-shaped, then you can apply these methods, but what if it's not? And that's where we are now. So the first point is tells you to Google Chebyshev's. There's an algebraic relationship that deals with the variable k. And the relationship I'm looking for is this one, 1 minus 1 over k squared. That is the amount of data, the percentage of data that has to lie within k numbers of standard deviations from average in any distribution. Now, what's interesting about this is I then compare it down here to a certain number of standard deviations. So let's just do this. Number of standard deviations. Okay, here we'll do bell-shaped. And here we'll do Chebyshev's. Okay, and then I got 1, 2, 3, 2/3 and a half. 1, 2, 3, 2/3 and 1/2. Okay, now we know from class-ish that within bell-shaped data you get about 2/3 of your data. So I think the rule that they use is 68% is the general percentage of data. Within 2 is 95%. Within 3 is about 100%. Within 2/3, I like this one, it's about 50%. Roughly half, the middle half of your data is within 2/3 of a standard deviation. I'm going to let you leave that one open. I put that one up for extra credit, so I'll leave that for you. You can try that one. Now, Chebyshev, the way you get Chebyshev's percentages is basically you run these numbers into this formula. So you can see that, well, let's just see. So within one standard deviation of average, within one standard deviation, what percentage is going to be in there? Well, it's 1 minus 1 over 1 squared, which is 0. So what Chebyshev says is you can't guarantee there's any data within one standard deviation. So the first thing you say is, well, duh, thanks, comrade. But then you realize, well, wait a minute, that could be useful. I mean, if you can't guarantee there's any data in there, this accounts for a worst case scenario with respect to variation. Maybe you do want to talk about not having any data within one standard deviation to make sure that your precision is wide enough to encounter the lion's share of data. So let's keep going and see how far out we have to go to get certain amounts. Notice that 0 doesn't contradict the 68. At least 0% needs to be. 68 is at least 0. Or I should say 0 is at least 68. Time out. Forget that I said both of those things. At least 0% includes 68%. So they don't disprove each other. This is just a less general, a less specific form than the empirical rule. Okay, 95% when it's bell-shaped. How about when it's not? Well, you got 1 minus 1 over 2 squared, which is 1 minus a fourth, which is 75%. So again, you can guarantee that 3/4 of your data are within 2 standard deviations. That's not bad. It's not 95, but this is even for the most possibly skewed data set you could imagine. Even for the most possibly skewed data set you could imagine, you could still guarantee at least 75% in there, if not more, no less, but at least that. Pretty rad, pretty rad. Within 3 standard deviations, 1 minus 1 over 3 squared. That's 1 minus a ninth. A ninth is about 89%. Again, not too shabby. 100%, yes, at least 89% includes 100%. Not too shabby, not rad at all. Here's where stuff starts to fall apart. Within 2/3 of a standard deviation, 1 minus 1 over 2/3 squared. Now, you don't have to look very hard to realize that this is 1 minus 9/4. 1 minus 9/4 is 1 minus 2.25, which is 1.25, but it's negative, which means negative 125%. So one of the problems with Chebyshev is that it only really gives you useful data when you're outside of one standard deviation. So you wanna just be aware of that. The same kind of thing happens with 1/2 of a standard deviation. Once you get down below 1/2 of a standard deviation, yeah, it's meaningful in the bell curve, but it's not meaningful at all with Chebyshev because the mathematics falls apart. What would it be for 1/2? Is it 100%? 1 minus 1. No, it's 300%, isn't it? It's 1 minus 1 over 1/2 squared, which is, yeah, 1 minus 1 over a fourth, which is 1 minus 4, which is negative 300%. Yeah. So, you got some issues as far as mathematics issues. The mathematics itself is fine, but the applications of it fall apart when you start talking about numbers of standard deviations less than 1. So, I hope that helped, and we'll see you in class.